41 through 44 and number 7 should have been done using this method, okay? The long way, right? What I said yesterday is when the direction said use the definition of the derivative, which is pretty much word for word on 41 through 44, right? Use the definition of the derivative. That is this right here. Those were not about putting in two really close points. Those were not zooming problems, okay? Those were working it out like this, like we did yesterday. Now this one's a little different than the one we did yesterday was x squared plus x, not 2x. So we had 5 for an answer instead of 6. And then we did this one where we got 70, and we plugged it into this, and you should have this work. Now, so that's what I was looking at. I was really looking at 41 through 44, and I was really looking at number 7. And some of you were lacking quite a bit in that area. If this was a quiz, and we had a problem about definitions written. Now, it's the first day we've done it, okay, so I get that. But some of your stuff would be quite lacking. Some of you are pretty good at algebra, and I could kind of tell that you had skipped a few steps in here. You know, I write out all those different steps and so forth, and you could probably go through there and, you know, do some of that algebra in less steps than what I have, and that's fine, you know. But expect to have to do this on the next quiz, which is around next Tuesday or so, at least once, if not a couple of times. Okay, having to go through this process. And we're going to do a couple of others here today. So that was the big deal on the homework, and that's what I was really kind of trying to pay attention to. So we talked about algebra versus calculus, average rate of change versus instantaneous rate of change. This is what we put in our notes yesterday. Slope between 2 points is average rate of change. We could write it like this. We could also write it like this, f of a plus h minus f of a. The 2 points here are a and b. The 2 points here are a and a plus h. We call that the difference quotient. Then if we add the limit into there, one of your questions asked about that said, what's the difference, or how are average and instantaneous rate of change related? Well, the difference is instantaneous rate of change is at an instant. It's the limit of the average rate of change as the 2 points become 1, as the 2 points get closer and closer to becoming 1. And that's what a limit is. As this approaches, as h gets closer and closer to 0, means the distance between the 2 points gets less and less all the time. So this is in the notes. I posted those. If you were gone yesterday, I posted these up on the website under the assignment page. And then, of course, you have the video as well. All right, so the definition of the derivative is this right here. It's made up of 2 parts. The difference quotient, which is the slope between 2 points, and then the limit, which as h goes to 0 means those 2 points get closer and closer together. So we worked out a couple of examples. So let's talk about this problem real quick. A few people asked me about number 6. Was number 6 the one about the equation of the tangent line?
Yeah.
Well, see, that goes along with what we did yesterday. Okay, number 6 just goes along with what we did yesterday, which is they give you this function and they want the equation of the tangent line at the point 280. So that would just be y equals, here's our derivative, we already did it, so you don't have to go do it again, or you can look back in the example, whatever, but we already did the derivative at 2, so that'd be the slope. So it'd be 70 x minus 2 plus 8. So there was number 6, that's all you had to do for number 6, right? We'd already worked out the slope at 2 when we went through this process yesterday. So there'd be the tangent line equation. Okay, and then we had, was this number 11?
Yeah.
Was this the one that had this picture?
Yes.
And so this was just like average rate of change and so forth. So they said like between 8 o'clock, which would be here, and 2 o'clock, which would be here. So the average rate of change would simply be the slope of that line. So the rise, it goes up from, it looks like it goes up from about $5.50, because this would be $5 right here. And it goes up to, it looks like it's a little past 11 on mine. In your book, it was kind of hard. I was helping somebody this morning, and it looked like it was 11, but they called it 11 and a quarter, because this would be 11. This would be 11.50. So in the answer book, they were calling it 11 and a quarter minus 5.50 for the rise, and then the run would be from 2 o'clock to 8 o'clock, which would be 6. So you just divide those. right? Average rate of change. And then they wanted the instantaneous rate of change at what? 9:15,
Yes.
which would be this first, so right here. So how would you do that? Yeah, just draw a line in here and try to do a rise over run. Right? And the answer's in the back. I don't know what they had, but just understanding the difference between average rate of change, which is just the slope between 2 points, and instantaneous rate of change, which is the slope of the tangent line. Right? So just different kinds of questions, but asking the same, asking about those two connections, these things we had back here. Average rate of change, instantaneous. Okay? This is not number 13, but it's like number 13, right? So I just wanted to throw it out there. So here's where they give you an H value. So now we can do that formula that's f of a plus h. Just the average rate of change is all that is. It's just the slope between two close points. In this case, or doing f of b minus f of a, f of b minus f of a over b minus a. Doesn't matter. It's just slope between 2 points. So they want to do h to be that. So 2.001 and 2 would be our 2 points. So you take those values, plug them into this function, get your values here, and this is what I came up with this one. So that's what you were supposed to do at 13. Very similar kind of thing. They give you h as 0.001, and you just do that. Okay? All right, let's talk about number 43. I'm skipping over 34 and 35. We're going to come back to them. Okay? We're going to come back to them. All right. So 43, f of x is it x cubed? Yep. Okay. Now make sure I'm kind of following along here. Okay. So, and we're supposed to find f prime at 4. So, and it said use the limit definition, right? So, f prime of 4 according to the definition, and again, if we come back to this, let me open up the one from yesterday. Okay, and if we look at our points here, okay, and there's our tangent line, okay, and as h approaches 0, okay, we have this thing right here, the limit definition, and I lost that. Okay, so there is our limit definition right there. That's the definition of the derivative. Right? H is approaching 0. H is this distance in between the 2 points, a and a plus h. So as that's getting closer to 0, our green line, our average rate of change, our slope between 2 points is getting closer and closer to our instantaneous rate of change. And if h could ever get to 0, that's what it would be, but that's what it's approaching. We're going to talk a lot more about limits the next couple of days. They are kind of hard to get a grasp on sometimes. Okay, so we're trying to find f prime of 4. So our 4 would be our a. So we put our 4 right there in place of our a. So limit as h approaches 0, f of 4 plus h minus f of 4 all over h, which would equal, let's write it off to the side here, limit as h approaches 0. What's f of 4 plus h? 4 plus h cubed. It's like the German short hair. It's like the peanut. If I do f of peanut, I did a peanut this time. If this is my function x squared plus 2x, f of peanut is peanut squared plus 2 peanut. Right? Whatever's inside the function goes in place of the x. Goes in place of the x. So 4 plus h goes in here in place of the x. So 4 plus h cubed. And then minus f of 4. 64, 4 cubed, all over h. Use Pascal's triangle or just FOIL it out. It ends up being, what would it be? 4 cubed is 64 plus 48 h plus 12h squared plus h cubed and then minus 64. Right? So make sure you can FOIL that out. 4 plus h times 4 plus h times 4 plus h. Use Pascal's triangle, whatever. But you've got to be able to do that algebra piece of that. The 64s cancel. Okay? And that's a good thing. And so we get limit as h approaches 0. What's left is this right here. We can do what with that? Take out an h. Or we can just divide each of those by h. That works too. So it's 48 plus 12h plus h squared is what we end up with, right? If we factor out an h, we can do it that way too. Factor out an h, all divided by h, but then the h is canceled, so it's the same idea. Okay? And now what?
Assume H is 0.
Now we can assume h is 0. Now we can go ahead and let h be 0. Now what does that mean? That means the 2 points actually become 1. The slope calculation doesn't work with just 1 point, but because we've done the algebra to make the h's cancel, we actually can make it work. And so we can actually plug in a 0. Okay? And so that makes that go away, that makes that go away, and we get 48. Now, if you think about it, the x cubed graph, what does that 48 mean? What's that mean? Slope of the x cubed graph at 4. So if you think of the x cubed graph, it comes up, it's flat, it goes like this, and out here at 4, does it make sense that the slope might be 48? It's getting really steep, and so that makes perfect sense. We would get 48. Okay? And that is the slope at that point. All right. So that's what 43, 41, and 42 are simpler versions of that, just because they had squares, and 41 didn't even have much at all in it. Didn't take much algebra showing at all. But, you know, some of you, it was pretty bare bones the amount of work you had on this one. This is what it should look like. Okay? So we'll get to 44 in a second. I want to talk about this right now. I want to give you just a second. You can just write it down in your homework or off to the side where you got some room. Right now, if I give you this function right here, how many different ways can you think of that we have learned this year to find or estimate f prime of 1? So just think about it for a few seconds here and just jot down how many different ways you could find or estimate f prime of 1 with that function. All right. What's 1? Okay, graph it, and it actually would come down like so. Whoops, that's bad. It would come down like so and cross there at 1. How did I know it was going to do that? I've seen it a million times. How did I know it was going to do that?
If you plug in 1 to the X, it's 0.
Yeah, I didn't plug in anything though, but you're right. I could have just started randomly plugging in numbers. Right?
Yeah.
So what are its roots? Where's it going to equal 0?
0.
0 and 1. And I knew it had a positive leading coefficient, so it's got to go up, right? So it was going to cross the 0 and 1. Okay, anyway, doesn't really matter, but we could have graphed it, right, by hand, from memory, the way I said, or with a calculator, and we could draw a tangent line, right? So we could draw a tangent line. So that's definitely one. Okay, what's another one? Zoom in. So I could have done f of 1.001 minus f of 0.999 maybe over 1.001 minus 0.999. Right? Pick two really close points. Do a slope. Okay, what else? Definition of the derivative. I could have went f of 1 plus h minus f of 1 all over h and done the limit as h approaches 0. Any others? That's pretty much it, right? I mean, anything else would be variations off of those, probably. Right? So draw a graph, do a tangent line. I mean, I suppose calculator actually can do it. You know, we just type it in. Right? So those would be different ways we can find or estimate f prime of 1. Now, these first two are estimates, right? This one's a really rough estimate. This one's a better estimate, right? Really good estimate, as a matter of fact. If we put more zeros in there, get closer, it'd really be a good one. And then this is exact, right? This gives us the exact slope at 1, because we let h go to 0, because we let the 2 points become 1. Okay, I just kind of put this all together, put it in perspective a little bit, think about the different things we were talking about. And then, of course, why do we need f prime of 1? Well, one great example that we keep throwing in there is this one, right? Find the equation of the tangent line. Right? Find the equation of the tangent line to that function at 1. Well, you need the slope at 1. How do you get the slope at 1? Well, it depends on the problem. Depends on the problem. You know, depends what information we have, which one of these we might use. Right? I guess there would be another one. Maybe I knew the f prime graph. Now, I didn't really tell you that. Do we have that information? All I gave you was f. But if you had the f prime graph, you could just go to 1 and see the y value, right? The f prime graph, the y value of 1 would be the f prime of 1, right? So you could throw that one in there, I suppose, as well. But you'd have to have the f prime graph to do that. Now, what we're going to get to today is, boy, it'd sure be nice to know an f prime equation, right? If you knew this was the f equation, it'd sure be nice to just know an f prime equation, because then couldn't you just plug 1 into it? So we're going to know by the end of the day, we're going to know the f prime equation of that one right there. Okay? All right. So, gives you something to look forward to. All right. Talk about a couple other things here before I do the next homework problem I want to work. This is an alternate form. I have it up on the board here. This is an alternate form of doing a derivative at a point A. So we've got this one. This is the one we use 99% of the time this year. But every once in a while, this version pops up. And if you look at my picture, all I did was rename the pieces from what we did yesterday. Instead of calling the points A and A plus H, I called them A and X. And then instead of letting H go to 0, which is what let A and A plus H get really close together, I just said I'm going to let X get closer to A. So it's the limit as X approaches A. And then my y values would be f of x and f of a. So when I subtract my y's, I'd have f of x minus, it's kind of like f of b minus f of a over b minus a, in a sense. But when it's written, we usually use x there. So that's all it is. So it's still the slope formula between 2 points, a and x. And we let the second point get closer to the first point. We let x approach a. So it's just the same exact thing. Slope between 2 points, let the 2 points get closer and closer and closer. Okay? It's just an alternate version. The downside, which we're going to see in a few minutes here, the downside of this version, it's only good for the slope at a point. this one, we're going to make just a little bit of an adjustment to this, and we're going to be able to find the definition of the derivative for all x. And that's what we're going to do to get that equation for that guy right there. That's how we're going to find f prime of x. Instead of f prime of 2 or f prime of 1, I mean, imagine number 43. Imagine number 43 here, we wanted f prime of 4. And then what if I said, oh, what's f prime of 2? What do you got to do? You got to do it all over again. And then I want f prime of 3. You got to do it all over again. And really get to be a pain. It'd be nice if we could just find f prime of x, an equation for f prime. And then you want f prime of 4, you just plug in a 4, plug in a 3, plug in a 2, you get the slope anyway. That's what we'd like to do. We already have one of those, right? If f of x is sine x, what's f prime of x? Cosine of x, right? And we have another one. If f of x is e to the x, what's f prime? It's its own, no, e to the x, right? It's its own derivative. If f is e to the x, its derivative is e to the x, right? We already talked about a couple of them. So it'd be nice to have other ones. Okay, that's what we're going to go to today. Okay, so anyway, so this one, this is an alternate form of just finding the derivative at a single point. It's not something we use that often, but it'll pop up once in a while, so I'll talk about it and say, hey, remember, this is that alternate form of the derivative. Okay. All right. So, next thing I want to talk about is some notation, and then we'll get back into a couple of homework problems again. But I want to talk about a little bit of notation here. Okay. So, starting up here in the left-hand corner. Okay, so starting in the left-hand corner, this is how we've been writing it. We've been writing, okay, if f of x is equal to sine x, then f prime of x is cosine x, right? And so we wrote that like that. And we had to write two different things. Okay, so that's what we've done so far. And then if you go over here, and then now you go to the middle on the top, sometimes we're not going to write it in function notation. Usually it's in function notation, but we might use y instead of f of x. So we might say y is equal to sine x, so therefore y prime would equal cosine x. So we're going to get into that using the y sum instead of f of x. Okay? And here's a new notation right here. This is called Leibniz notation. Now, Gottfried Wilhelm von Leibniz is one of the two people that are kind of credited with developing the ideas that are calculus, along with Isaac Newton. You've probably heard of Isaac Newton. Leibniz, maybe. Okay. They kind of were working on it separately, but they kind of came to some of the same conclusions and some of those things. Eventually became what is calculus. They say invented calculus. Well, it's not like one day they just said, aha, here it is. I mean, it's more like they were working on these different ideas, and then eventually it kind of came together. Connections were made and so forth. Well, anyway, Leibniz used this notation, dy over dx. What you want to understand is that y prime and dy over dx that's exactly saying the same thing. Those are exactly the same. They both mean the derivative of y. The nice thing about the Leibniz notation, a couple nice things about the Leibniz notation, is it tells you what the input variable is. It comes from slope. Dy over dx is like, the Greek letter delta, the triangle, right? What does that mean? Delta y and delta x. Change in y and change in x. That's what slope is. The change in y over the change in x. So it's a Greek letter d, basically. So dy over dx. Think change in y over change in x. But you can also think of the d as derivative. You can think of it as derivative of y with respect to x. So the bottom, just think of that as being, hey, that's the input variable. So if we had a function, remember we did that function yesterday, dt, right? D of t, the distance of that professor. And we did the derivative as d prime of t. Well, if we were going to do Leibniz notation, that would be dd, derivative of d, with respect to t. So it would be dd over dt. That would be the same as d prime of t. Okay, the derivative of d with respect to t. Again, nice thing about Leibniz notation is it tells us what the input variable is. If we just say f prime or y prime, we don't really know, is it with x or with t, what is it? That's one nice thing about Leibniz notation. So you're going to start seeing that from time to time. So you've got to know what that means. It just means y prime. That's all it means. Or in this case, this one just means d prime. That's it. But one of the things that Leibniz notation allows us to do is we can take this guy over here, instead of having to write out both parts of it and say that, okay, if f is sine, then f prime is cosine, we can just write this, which is saying the derivative of sine with respect to x is cosine. So when we write our rules for derivative, which we're going to come up with some here in the coming days, we can write them out like this all in one line. And this says the derivative of sine is cosine. And really, where that comes from, if you think about why that is, it's kind of like doing this. If I think about dy over dx, and you know how in fractions, like if I have 2x over 3, you know how you can take that x and put it out in front and write that as 2/3 x like that? You know what I'm saying? Well, when I have dy over dx, and I could also do that same thing, I could go like this, and it's like I could take that y and just put it out in front. It's kind of the same thing. It's still dy over dx. And then if y is sine, I can just put sine there in its place, you know what I mean? So this is like saying, it's like the signs on top. So it's kind of those same rules of fractions we had. So it's like saying the derivative of sine with respect to x, that's all the bottom means, is with respect to x. It's not a divide here now, guys. It's not divide, okay? It just means with respect to x. This is just saying the derivative of sine with respect to x is cosine. Okay. Yeah, don't think of this as a divide by sign here, even though it comes from the idea of slope, which is change in y divided by change in x, right? It comes from that. But as a notation, it does not mean divide, okay? All right, so anyway, you're going to see that. Now, second derivative. So far, we've seen f double prime. And, of course, if we're using y, that'd be y double prime. But here's the Leibniz notation for second derivative. It does not mean squared. Okay, it does not mean squared. The 2's just mean second derivative. That's all they mean. 2's just means second derivative. And again, where does it come from? It comes from the same thing we're doing here. The derivative of, or excuse me, the second derivative is the derivative of the derivative, right? Well, using this notation we did up here, we could write the derivative of the derivative this way. We could say the derivative of the derivative. That's the derivative of the derivative. Well, you see how it kind of looks like d squared y over dx squared, kind of. I mean, that's where it comes from. But again, it's not squared. Things aren't squared. This is a times. This doesn't mean times. It's f of. It's dy. It's a derivative of. So just understand when you see this, it just means f double prime, y double prime. Just notation. Okay? So, didn't want to introduce that early on, back when we were in chapter 1. We wanted to get used to the idea of prime, what a derivative was, whatever. Okay, but now it's time we recognize that if we see it. All right. Now let's do number 44. Okay, shift gears here a little bit, back to the home. All right, so in 44, we're supposed to find f prime of 4 on this function, right? Now, the algebra we've stuck with so far, has been just FOILing, factoring, canceling. There are 3 types of algebra things that are going to be important for you to do before our next quiz. There are 3 types of algebra techniques you're going to have to do before our next quiz. One is factoring and canceling. That's all. Nothing be, he had migraine. I don't even know why he would try to be.
I thought he was just sick of it.
Yeah, I had enough. Well, maybe it could be. No, I give credit for trying to get it out. Yeah, I could. All right, so 3 algebra techniques you need to be able to do. One is factoring and canceling. That's the easiest one. Second one is, we find here, which is get a common denominator. Bow tie. Mrs. Payne likes it. Right? Kind of the same thing. Now, the only thing about bow tie is it doesn't give you the least common denominator, but it actually doesn't really matter. Right? Bow tie, if I had 1/2 plus, that's a bad example. If I had 1/6 plus 1/8, right? What's the least common denominator between 6 and 8? 24. So the least common denominator method would say, okay, I got to get 24 on the bottom here. So I'll take this times 4, top, bottom. I'll take this times 3, top, bottom, right? And you would change that into 4 24s, and you'd change that into 3 24s, and you would get 7 24s, right? The bow tie method says you take this times this, right? So you'd have an 8 on top of that one. And then you would take this times this, 6 times 1, so you'd have 6 on top of this one. And then the common denominator is 6 times 8, which is 48. And then you would add those up, and you would get 14 over 48, but then you'd have to reduce it, because it's not a least common denominator, right? But at least it does work, where you just multiply, right, and put, so this number times that number, put it up there, this number times that number, put it up there, and then the bottom multiplied together is your denominator. Okay, so least common denominator method or the bow tie method, they're kind of the same idea. Well, you're going to have to be able to do that with some algebra here. The third algebra method we're going to do involves square roots, and you're going to have to be able to multiply by the conjugate. Okay, the conjugate. Now the conjugate is, if I have a plus b, then the conjugate of that is a minus b. Because what nice thing happens when you multiply a plus b times a minus b? You get a squared minus b squared, and the outers and inners drop out. Why is that a good thing? Because if you have square root of 3 plus 2, if you multiply that by square root of 3 minus 2, what do you get? 3 minus 4, which is negative 1, and the square roots are no longer there. So if you were doing a thing where you wanted to rationalize the denominator, you wanted to get the square roots out of there, you could take the top and bottom. If you had square root of 3 plus 2 on the bottom, you could multiply the top and bottom by square root of 3 minus 2, and that would make the square roots disappear from the bottom. So that's multiplying by a conjugate. So those three algebra techniques are techniques we're going to need to be able to do. Okay? Might be able to find some stuff. I don't know if that IXL has some review of that. I've got some review things I can give you too as far as practice that. But so you'll see where it comes in, because right here, so this is what I really was paying attention to when I was looking at homework, and we had a lot of trouble on this. We had a lot of trouble on this. Okay? So here's my definition of the derivative. I always think it's important to write that out with your F notation, right? So we want f prime of 4, so it's that. Notice, the reason I think it's so important to write this out, because this doesn't matter what the function is. It doesn't matter what the function is. This is going to look the same on every problem. If you go back to 43, that's exactly what 43 looked like. And 42 and 41. They all looked like this on this line, because they were all finding f prime of 4. Okay? So when you're finding f prime of 4, no matter what function you're doing the derivative of, it's going to look like that. Okay? Now we can say, all right, now let's write it out. What is f of 4 plus h? Well, this is the peanut. 4 plus h gets plugged in for x. So that's 2 over 4 plus h. Minus f of 4, which is 2 over 4. Now I could reduce that to 1/2, or I could leave it. Doesn't matter. Okay? So now I need, this is where I need a common denominator. I need to bow tie this, or get it, whatever. So if you're going to bow tie, you would take 4 times 2, which is going to be 8. Right? And that goes on top on the left. And I'm going to take 4 plus h times 2, which would be what? 8 plus 2h. I'm taking 4 plus h times 2, right? Right there. Took 4 times 2 right there. Now don't forget about that minus. And I better put parentheses around that, because I got to distribute that minus. The most common mistake we make in these problems is we lose track of a negative, because it's the 8 here minus whatever we get up here. So that's got to be in parentheses. And then that's all over 4 times 4 plus h. The bottom multiplied together. That's a bow tie. Okay? So 4 times 2 goes on top, 8. 4 plus h times 2 would be 8 plus 2h. I'm going going to subtract those because that minus sign goes all over that. And then that's all over h. Okay, now what happens on top here? You're going to get 8 minus 2h. The h's cancel. That's a good thing, just like when we were doing the other factor stuff. Some things was canceling for us. So we end up with negative 2h over, I'm going to go ahead and distribute that through, 16 plus 4h. Okay, and I got this h on the bottom. Now what? You can cancel out the h's. I like to think of it as invert and multiply. I got this thing up here divided by h. That's the same as timesing by 1 over h, right? Invert and multiply, but you're right. The h's cancel. We do have to be careful with that a little bit. Make sure it's in the right spot there. But dividing by h is like invert and multiply. So those h's do cancel, yes. And so we end up with, I forgot my limit here, got a little lazy. So I end up with negative 2 over 16 plus 4h. Like so. Right? And now we can let h be a 0, right? Because think about it. Until then, we always have this h down here on the bottom. So if we let h be 0, we would be dividing by 0 all the time. Even right here, we'd be dividing by 0. But once those h's canceled right there, that allowed us to now say let h be a 0. And so we get negative 2/16, which reduces to negative 1/8. Here's the graph of 2 over x. It looks like this. So out here at 4, seem reasonable. The slope is negative 1/8. Negative 1/8. Okay. What's that? I have an h in the denominator, but if I put a 0 in there, I get 16. Yeah, I'm just putting a 0 in for 8, so 16 plus 0 is 16. Yeah. So yeah, it's okay to have an h in the denominator. I just can't have 0 in the denominator all by itself. Okay? So you're going to have to be able to do that for those type of functions. Okay? All right. Quick little practice here of the example I was just talking about. So here would be a couple of these algebra things I was just mentioning. So we just got done doing a bow tie situation, and I told you about the conjugate. So what would the conjugate be on this one? Root x plus 2. And I'm going to take the top and bottom times root x plus 2. So we'll just take a second here to practice this real quick. So that would end up giving me 3 root x plus 6 on top. And what would I end up with on the bottom? X minus 4, right? It gets rid of that radical for us. Now what we're going to find here, we're going to do a problem, well, you're actually going to do a problem as part of your homework, where you're going to do the long way, okay, on a problem that's going to have square roots in it. Okay, so when you do this technique here, you're going to have some square roots that you're going to have to do, so you're going to have to multiply by the conjugate. Now, it's not always going to be the bottom. Sometimes the square roots are on the top, and we want to get rid of those. And what do we mean by get rid of those? Well, what we want is we want things to cancel. We want that h to cancel, basically, is what's happening. So you see the radical in there, you're going to multiply by the conjugate. Okay? And then I gave this problem right here. So, just an algebra example. So, what would I get on top if I bow tie? Well, if I bow tie here, I'll have 3y minus 2x all over xy, right? Which is the bottom multiply. So it's a cross multiply, but but where does it go? You always got to remember, you take this one, the bottom, times the one on top, and that's where it goes, is up there. So y times 3 is 3y up there. X times 2 is 2x over there with the subtract, and then the bottom is that. So what allows us to do is take two fractions that are being subtracted or added and turn it into one fraction. And then that's helpful because now we can invert and multiply. So now we can invert and multiply with the x squared, and of course nothing really cancels on this one. So in this case it would end up being just 3y minus 2x all over what? X cubed y. but it allows us to take, anytime you have, it's called a complex fraction, anytime you have a fraction within a fraction, we don't want that, right? We want to write it as just a single fraction. So that's what it allows us to do. But for us, what it's going to allow us to do is going to allow some nice canceling to happen. So these three algebra techniques, for us, in our problems, is going to allow some nice canceling. In this case, it allowed those 8's to cancel out, which then allowed these h's to cancel. Okay? And that's what's going to happen with those three algebra techniques. Okay? All right. Now let's talk about 34 and 35. Not a real big deal right now on 34 and 35, but the next couple days we're going to get into this a little bit. So, and I had several people come to me and ask me about this, were really doing some good thinking on this. And the term I heard from somebody was unpacking. They were trying to unpack this definition. That's exactly right. That's exactly what these problems are. It says in the direction, it says that the limit shown is f prime of a for some function f and some number a. So they're telling you that the limit they're showing you right there is this thing. So let's just look at the pieces. They want you to find what f and what a are, and then the last part I don't really care if we do right now, quite honestly. I don't think anybody probably tried too much. But so doesn't this look like that definition over there? What's what? What's changed? What's this thing? H. That's the H, right? Let me get some color. So this is like the H right here, and that's like the H, and that's like the H, right? So what's the A got to be? Doesn't the A have to be 9? Because the first part of it is the A plus H. Now let's go back to what we did over here. Let's go back to right here. Let's pick one that we can see easier. Let's go back to this one. So pretend I had just given you this. Okay, this is what we're talking about. We're just talking about working backwards. Pretend I had just given you this limit right here. Well, right when you saw that 4 plus h, that would be a big hint that, oh, this must be the derivative at 4, right? Why? Because what do? We do 4 plus h, and then what do we do with that 4 plus h? We plug it in for, we plug it into the function for the x. So think about that. The 4 plus h goes in where the x was, right? Let me say that again. The 4 plus h is going to go in place of the x. So when I see 4 plus h cubed, that tells me wherever the 4 plus h is, what must have been there before I plugged in 4 plus h? The x, right? The 4 plus h goes in for the x. So when I see this, I'm thinking to myself, that function must have been x cubed. If I'm thinking backwards, I'm thinking that function must have been x cubed. Because I know 4 plus h goes in where the x was. And I see 4 plus h there. Go back to this one. I see 10 times 2 plus h plus 15 times 2 plus h squared. I know that 2 plus h goes in where the x was. So this function must have been 10x plus 15x squared. Well, it was t, not x, but you get the idea, right? So I can tell, just looking at this limit right here, I can tell what my original function must have been. Because wherever the 2 plus h is where the x had been. So when I'm on this problem, and I'm looking at this, here's the 9 plus h. So what must my function have been? My function must have been square root of x. Because the 9 plus h goes in where the x had been. So my function must have been square root of x, so that when I did f of 9 plus h, I plugged the 9 plus h in there, and that gives me square root of 9 plus h. So you see what I mean? So that's what you focus in on when you're looking at this backwards. Now, the 3 might have thrown you off, but actually if the function is square root of x, this is f of a plus h minus f of a. Well, in this case, that'd be f of 9. Well, what do you get if you plug 9 into the function? Square root of 9 is 3. Oh, yeah, so this was really square root of 9 plus h minus square root of 9, but they went ahead and simplified it Square root of 9 is 3. And then all over h. So that's what this problem is. Now, they didn't have you go ahead and finish it. They said, what did they say? Draw a graph of the difference quotient or something? Is that what they said? They said draw a graph of this. I don't want to get into that right now, so we're not going to worry about that. We actually could work this out the long way now that we know about conjugate, right? Here's where we would use a conjugate. This, matter of fact, you're going to have a problem like this on the homework. But, so if you had this over h, and we were trying to do this limit as h approaches 0, here's where we would multiply by the conjugate. What would be the conjugate of the top here? Careful. Think of this as your a minus b. So we do 9 plus h square root plus 3. We would take the top and bottom times that. There's our conjugate right there. So we got root minus something. The conjugate of that would be root plus that something. So we'd leave the 9 plus h in there. We think of this as one thing. So we got a root minus 3. We multiply by root plus 3. Because what would happen if you FOIL, I'm not going to work it all the way out, but what if you would FOIL this? What would happen? Well, this times this would just be 9 plus h, and then minus 9, because we know the outers and inners would cancel out, right? That's what happens when you do a conjugate. Well, look how nice that is. See that? The 9s will cancel. Geez, we're almost done now. Might as well finish. Right? 9 plus h plus 3, right? The bottom I'll just leave, kind of worked out. So the 9s cancel, then the h's cancel, we end up with that, right? And then what can we do? We can plug a 0 in for h. Put a 0 in for h, what do you get? Square root of 9 is 3. 3 plus 3, 6. We get 1/6. And what is that? That's the original function was square root of x at 9. Here's the square root of x. It's the top half of a parabola. Out here at 9. Does it look like the slope might be 1/6? Seems reasonable. Seems reasonable. You didn't have to go through all that, but you're going to for tomorrow, right? We just talked about conjugate. So if you were doing a square root function and you were doing the derivative and you set up your definition of the derivative here, it would look like this. The algebra we would need on that would be the conjugate. The conjugate. So we've done common denominator, bow tie. We just did a nice conjugate example, and we did another conjugate, but that's what it'll look like. Okay? All right, what about this one? How does this look like this? Well, again, I always look for the a plus h, the a plus h, the a plus h. Where's the a plus h here? How about right there? Isn't that a plus h? 0 plus h, right? And then what must this have been over here? Cosine of 0, right? It's f of a plus h minus f of a. So that must have been 0 plus h. So the a must have been 0. And the function was cosine of x. The a plus h gets plugged in where the x was, where the x used to be. So cosine of 0 plus h, the 0 plus h is like the peanut, the German short hair. It got plugged in for the x. So it must have been an x there. So the function's cosine x at 0. Okay, this one we don't have a way of working out. We don't have any nice algebra we could do to this. So we're not going to worry about it right now. But that would be the slope of cosine. Now, to be honest, you should just know that. Here's a cosine graph. And we're doing the slope at 0. What's the slope at 0 on the cosine graph? Right there. 0, right? So we would happen to know it just because of that. But anyway, don't worry about that other part. I just wanted you to be able to understand that this limit matches this definition. And we can kind of work it backwards and see what the f was, what the a was. Okay. All right. Here's the new thing for today. So let's go to your notes here and let's talk about this. What I was saying earlier. What we'd like to do, wouldn't it really be cool if we could get a derivative formula? Wouldn't it be nice if we could, now you say, well, we got this, yeah, but that just finds the derivative at a single point. Wouldn't it be nice if we just get an f prime equation that we could just plug into to get our slopes? That would be great, and that's actually what we're going to do. So right now, the question is, what if f of x is x squared? And instead of finding f prime of 1, or f prime of 2, or f prime of 4, let's find f prime of x. Well, all we need to do is take this scenario. Hang on here a second. All we need to do is take this scenario and change the a to an x, right? All we need to do is we need to change that a to an x. So over here, we're going to write the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is the way I will write this definition from now on. I'm not going to write it with an a, I'm going to write it with an x. I mean, you still might see it with an a, but the idea is this would allow us to do the derivative for any x. Now, if we still want to do this and get the derivative at 2, sure, put a 2 in for x, there and there, okay? And we can still do it. So we can still do it like we did for our homework here. But I want to do it with an x in there. So all of the same things would work here. You got your second point. You got your slope between x and x plus h. You want to let h go to 0, right? It's the same exact thing. It's the same exact thing. We just changed the letter from an a to an x, okay? But how does that affect when we work it out? Well, it has a huge effect because, well, let's go through it. So, f of x plus h, so I have no number to plug in. Like before, we had a 4, right? We were finding f prime of 4, so we put f of 4 plus h minus f of 4. Well, now it's just going to be f of x plus h minus f of x all over h, right? So, that's our definition. So let's do this first part. Let's put that in a blue box. So what's f of x plus h? That means take x plus h and plug it in to this function for the x. So that will be x plus h squared, right? And that's in the blue. So that's basically the blue box right there. And then the red, what's f of x? Yeah, that's f of x with an x plugged in. Oh, that's x squared. Okay, that's easy. That's x squared. So that's the red piece. So instead of having all these numbers, we just have a lot of letters, right? That's okay. We can deal with that. So, keep writing my limit down here. What's x plus h quantity squared? X squared plus 2xh plus h squared minus x squared all over h. Now, the nice thing that was happening to us before was something was canceling, right? And in this case, it's still happening. The x squared's canceled, right? Now what? Factor out that h. Right? Which allows those to cancel. Which is good because now what can we do? Now it's legal to plug a 0 in for h. Because again, what does 0 in for h mean? It means the 2 points are getting close together, right? That's what h going to 0 means. The 2 points are becoming 1, which is what we want. The slope at 1 point, in this case, any point x. And you put a 0 in, and what do you get? Aha. So what we're saying is that if our original function is x squared, our derivative function is 2x, right? Using Leibniz notation, what we just said is that the derivative of x squared is 2x, right? Isn't that what we just said? The derivative of x squared is 2x. And if we want to reach back into, don't write this down, but if we want to reach back into some algebra, or excuse me, some chapter 1, here's f right here, x squared, right? And let's put f prime in there. F prime is 2x, which would come through like so. Does it look reasonable that that would be the case? You got f prime changing from negative to positive. What's that mean f is? No. F prime changes negative to positive. F has a local minimum. When f prime is negative, f is decreasing. When f prime is positive, above the x-axis, increasing. When f prime is increasing, which it always is, what's f? Concave up, which this always is, right? Seems to make perfect sense with what we learned on the chart back in chapter 1, but now we got this equation business going on. All right, well, let's do this one. Let's have some more practice. Some of you got 4 or 5 practices on the homework last night. Some of you didn't get quite that many. If you didn't, we're struggling with this a little bit. So now we want to get everybody on the same page. We want everybody to be able to go through this definition of the derivative. Okay? Got to be able to do that. A couple of questions on the next quiz that we'll be doing this. So let's do x cubed. Find f prime of x. So this would be f of x plus h minus f of x all over h, right? We're not doing f prime at 2. We're not doing f prime at 4. We're wanting to do f prime at any point x. So what's f of x plus h? What's f of x plus h? Take the x plus h and plug it in for the x. So it'll be x plus h cubed minus f of x. F of x is just x cubed all over h. What is x plus h cubed expanded out? Pascal's triangle will be really helpful right now. 1, 3, 3, 1. If you need to work it out longhand, that's fine, but we'll just copy down with us right now. X cubed plus 3 x squared h. Right. Now, you can just FOIL that. You can do x plus h times x plus h, get that answer, then take that answer times x plus h again. That's right, and you're going to end up with the same thing. And then don't forget the minus x cubed. And again, that's all over h. We can't put a 0 in for h right now because we'd be dividing by 0. That's no good, but some nice things are going to happen. We're going to have x cubes are going to drop out, which allows what to happen? We can now factor out an h. And we'll have what? 3x squared 3xh all over h. The h's will cancel. You can feel it coming, can't you? Some of you knew it was coming already. The excitement is building. Come on. Right? Limit as h goes to 0. So now you can put a 0 in for h. Want to just be 3x squared?
Yep.
Because that'll become 0. That'll become 0. So what we just said is that if we do using our Leibniz notation, the derivative of x cubed is 3x squared, right? That was so much fun. Let's do the derivative of x to the 9th. What is it?
9x to the 8.
It is. It is. Isn't that something? Look at that. F of x equals x squared. the derivative was 2x. Okay, big deal. We drew the graph, seemed reasonable. But then you do that one and you're like, wait a minute. That 3 looks like it just came down in front, and it looked like the power dropped by 1. Does that always work? Huh. Let's try this one. What's the derivative of x? Now, wait a minute. That's just a line. Y equals x. What's the slope of y equals x? 1. So we know that already, right? We know the derivative is 1 of x, right? Because we know that's a slope. Well, according to our little rule we think we've come up with, we would bring a 1 down in front, and then this would be x to the... Oh, did we? Huh. What's the derivative of 7? Well, what's the graph of y equals 7? Horizontal line. What's the derivative of 7? It's got to be 0. What's the derivative of 9? Derivative of 10. Derivative of a constant has to be 0. Does that fit in with this? Well, one way to write 7 is 7x to the 0, isn't it? Yeah. Isn't that 7? Yeah. So let's do that rule. Let's bring the 0 down in front. And drop the power by 1. Oh, but what's 0 times... Oh, 0 times whatever is... Oh, well, that worked too. Now, I would never use a power rule on that. If you ever do the derivative of a constant, it's 0. Derivative of constant is 0. Aha, that is actually called the power rule for derivatives.
What about fractions?
Fractions work too. We'll do an example here in a minute. But here's the power rule for derivatives. If you do now this is only for powers, not exponentials. Remember e to the x? What's the derivative of e to the x? E to the x. Some people want to take that x and bring it down in front. No. That's a different situation. That's an exponential. That's a number raised to an x. We're talking about x raised to a number. X raised to a number. If you have x raised to a number, the derivative is you can bring the number down in front and you can drop the power by 1. But it is really cool. I mean, this is just another really cool thing. Are you kidding me? You mean that for every one of these polynomials, that the slope can be found by simply bringing the power down in front and dropping the power by 1? Well, we saw it happen, right? We saw it happen over and over. It was because of that binomial expansion happening in there. And sure enough, it does. And that's one of the most useful rules we'll have all year long. It's a great, great shortcut. Now, you're going to get really happy with that shortcut, and you're going to be mad about having to do them the long way, right? Like on our next quiz, but you're still going to have to something. All right? Now, you asked about fractions. It works with fractions. It works with negative powers, okay? It works. The power rule works. Now, one of them you're going to do for your homework is square root of x, which is a fractional power, right? Square root of x is x to the 1/2 power. Now, you're going to have to do it the long way, but then we can check, right, and see, oh, yeah, we got it, just like here, right? We now know the derivative of x cubed is 3x squared. We can see, we checked it right there. I mean, we did it the long way, and sure enough, it was. Okay, now let's talk about some other situations then. Let's just make a little chart of little things that'll be nice to know that go along with the power rule. Because normally we normally don't have functions that are just x to the 5th or x to the 4th or x to the 3rd. They usually have a number in front or a number inside or maybe a shift this way or a shift that way or a shift up or a shift down, that kind of thing. So how do we deal with that? Excuse me. So here we've got a 5th power, but it's shifted 4 to the right. So think about what that would do to the graph. Or more importantly, what would it do to the slopes? If you just shifted 4 to the right, do any of the slopes on that graph change? The only thing that changes is where they happen, right? So if you had next to the 5th graph and you were here where it was kind of steep, now on this graph, that same slope would be shifted over 4. So it makes sense that the derivative of a shifted graph, if you shift the graph horizontally, the derivative is also going to be shifted. So the derivative is just what we think it might be. Bring the 5 down in front, leave the inside alone. You're going to hear me say that a lot. Leave the inside alone because the new graph, or excuse me, the slopes are going to get shifted as well. So anytime you shift a graph, you're shifting the slopes with it. Okay? So when I talk about do the derivative, a lot of times I say leave the inside alone. So we bring the 5 down in front and we drop the power to a 4. That is the derivative. Okay, what if you have a 3 in the front? Well, or in the inside? What's that do to the graph?
Shrinks it.
Shrinks it. Now we got a couple things going on here. So now where the slope was this, now it's moved in, right? So all those slopes are now moved in. So the 3 is going to have to stay on the inside to represent that shrink. But what happens to the slopes when you shrink or compress it in? They get steeper. They get steeper. And they get steeper by how much? By a factor of 3. So actually, this is kind of a weird one. When you multiply on the inside by a number, you do your normal derivative. So we bring the 6 down. And we're going to have a lot of time to talk about these and practice these and so forth. You'll bring the 6 down. The 3 will stay in there because everything's compressed in. So the slopes are now at new places, compressed in. We drop the power to a 5, but we have to multiply by, sometimes we say kick out. We have to multiply by a factor of 3 because by compressing, all those slopes got 3 times as steep. Think of a parabola, right? You get skinnier, you get steeper. So whatever that number's on the inside, it stays on the inside, but we have to kick out a multiplier by that amount too because the slopes are getting steeper. And so then you would probably write this as 18 and then 3x to the 5th right there. Okay? So that's the one thing we got to remember. So here's an example with sine. Again, what's that 2 in there do? It compresses, right? So what's the derivative of sine? Cosine. We're going to leave the inside alone. We always leave the inside alone when we do a derivative. But by compressing, what's it do to those slopes? They're steeper by a factor of 2. So we've got to multiply by a 2, or we have to kick out a 2 to accommodate. That's really the one where that matters. Okay? We got to kick out that 2 because it's making those slopes steeper because of that compression. All right? What about a 3 on the outside? That stretches vertically. So does that change the slopes? Sure. That's going to make them 3 times as much. But it doesn't change where they are or anything. So anytime you have a number out front, it's easy. It just stays there. It's got to stay there because all the slopes are going to be 3 times as big, right, when you stretch this way. So they're going to be 3 times as big, and then just do your normal derivative. So the derivative of sine is cosine. So anytime we have a multiplied number out in front, it just hangs out there, and then you do your normal derivative. So same thing like with 7x, right? The 7 would just hang out there, and then what's the derivative of x? Well, bring the 1 down in front, which is 1 times 7 is still 7, and then x to the 0. But what's x to the 0? So the answer is just 7. Now, to be honest, you shouldn't even think of the power rule on that. 7x is just a line. 7x is a line. What's its slope? 7. So what's the derivative of 3x? 5x. Negative 2x. Right? Anytime you just get x to the first power, that's just a line. So the slope is just whatever number's in front. Right? So that we shouldn't even think of the power rule, quite honestly, on that. Okay? The slope's just 7. And then what's the slope of 5? What's the derivative of 5?
0.
Right? And again, we shouldn't even think of the power rule on that. I mean, we could put an x to the 0 there, but 5, just a horizontal line, slope is 0. Okay, cool. So we've got a nice rule here where we can find a lot of different derivatives. Right? And then if we know the derivatives, now we want the derivative of 2, we just plug a 2 into the equation on the right. Plug a 3 into the equation on the right. That'll give us our slope. Okay? Chapter 3 is about finding a whole bunch of other formulas, but chapter 2 will have a few that we can deal with here. All right. Somebody talked about fractions, and we talked about negative power. So let's go through a few of those. So what if we have 1 over x cubed? Well, we can't do a derivative. Some of you might think, well, that's 1 over 3x squared. No. Just because you see a power somewhere doesn't mean you just do its derivative right wherever it's at. You've got to make it x raised to a power. So we would have to first write this as x to the negative third. So we got to write 1 over x cubed, we got to write that as x to the negative third. So then what's the derivative? Negative 3, careful, negative 4. You got to subtract 1 from the power. Negative 3 subtract 1 would be negative 4. Okay, and just leave it like that. You don't have to drop that x down to the bottom and make it negative 3 over x to the 4th or anything. Just leave it like that, it's fine. Okay, if you had to do some extra work with it, which we will later on, then you could, but for right now, excuse me, I would just leave it. Okay, what's the square root of x? X to the 1/2. So the derivative of that would be 1/2 x to the negative 1/2. 1/2 subtract 1. 1/2 subtract 1 would be negative 1/2. 1/2 x to the negative 1/2 is the derivative. Okay, what's the cube root of x to the 4th? The root always goes on the bottom, and any power that's in there goes on top. So cube root of x to the 4th would be the same as x to the 4th thirds. You'll find out, well, you can see it because of this power rule right here, that in calculus we'd much rather deal with powers than we would radicals. Much rather have them in power form. So the derivative, to the 1/3, 4/3 take away 1, 4/3 take away 3/3 would be 1/3. So there's the derivative. Okay, now, what happens if you have a polynomial? What happens if you have multiple terms added together? Well, it turns out that there's a rule that says that it's okay to do the derivative of each term individually, and that will give you your f prime, your derivative. So, we can do the derivative of this first one. Now, what did we say with that 3? Just hangs out there, right? So we bring the 4 down in front, so we'd have 12 x to the 3rd, because that 3 out in front would just stretch that x to the 4th graph. So the 3 just stays there because our slopes would be 3 times as much. And then minus 6x squared, right? And then what's the derivative of 8? 0. Remember, 8 is just a horizontal line if you're just looking at 8 by itself. Now, here's another thing. So this is interesting. So what if this would have been 3x to the 4th minus 2x cubed plus 10? Same derivative. What if this had been 3x to the 4th minus 2x cubed minus 12? Does that sound familiar, like something we've talked about before? Remember when we talked about the f prime graph and then tried to draw the f graph and we said we don't know where it started because all those different f's that are shifted up and down all have the same f prime graph? Well, that's what we're seeing right here. This plus 8 is just like a vertical shift. So if I change this to a bunch of different constants, those are all just vertical shifts of one another. They're all going to have the same slopes. So it makes sense that we just have that one derivative could represent multiple different original functions. Okay, good. Now, what about this? Yeah, so the reason I threw this one in here is we just got in saying if you're adding a bunch of terms together, you can just do their individual derivatives and add them together. So the question becomes, what if you're multiplying two things? Can you just do their individual derivatives? Could you do 3x squared times 4x cubed? Right? Because that's what each one of their derivatives would be, right? Well, that would multiply to be what? 12x to the 5th? Now we know x to the 3rd times x to the 4th is x to the 7th, right? We know x to the 3rd times x to the 4th is x to the 7th. So what should the derivative be? So did that work to do them individually? It did not. So when you're multiplying functions, you cannot do their individual derivatives and then multiply them together. That only works with add and subtract. With add and subtract, you can do their individual term derivatives and add and subtract them. But with multiply, you've got to simplify it out first. Now, I think, yeah, I had one here. Don't worry about writing this one down. But a person might think that the derivative of this is 3x squared cosine x, right? Do the derivative of that, do the derivative of that. No. We just saw down on there it doesn't work. We just saw that didn't work. So that doesn't work either. We'll have to have a special rule for that. Okay, that's chapter 3. So we won't worry about it right now. All right. So there you go. So let's summarize what we've done today. So we reviewed this whole average rate of change, instantaneous rate of change thing, right? 2 points, slope between 2 points. But if we let the 2 points become 1, we have this formula here where we can find the slope at a point. The long way of doing it. And so what we ended up with, we've done some examples the other day, so we want to find f prime of 2, we can do it. Of course, we now know that this derivative would be what right here? 2x plus the slope of 2x. 2x is just a line, right? Slope would be 2. We know that the f prime actually would be 2x plus 2. Now put a 2 into that. 2 times 2 is 4 plus 2. Oh, that's so much nicer than doing all that, right? But we're still going to have to be able to go through it. All right? So we know that. All right, then we did this one. We got 70. Oh, wait. Now we know that the derivative of that's actually what?
10.
Derivative of 10t is 10.
Plus 30t.
Put a 2 into that. What did he say? Did he miss it? Is he struggling? He said, well, I heard it. I heard when everybody said yes, somebody said no or something, and I thought it came back there. But put a 2 into there, we get 70. Okay? We get 70, which is what we found there. Okay? We talked about how we could do this with 0.01. Again, that's just 2 points being really close together. We talked about how many different ways we can find f prime of 1. Well, we got another one now, right? We can actually do the derivative. What's the derivative of x squared minus x? 2x minus 1. The slope of negative x, or the slope of x would be 1 minus 1. Now put a 1 into there, right? We can do that. So we just found another way we can do that. Okay, what's the matter here? Oh, why did I do that? I don't know. We talked about this alternate form. I wouldn't worry too much about that. We got some notation, some new notation here. And then we talked about this algebra with the conjugate and that kind of stuff. All right? So, and that's going to be a big part of your homework right here, this conjugate, and still doing these the long way. Now, there are going to be some where you get to do this new shortcut. Again, I'm going to say this just like I did yesterday. The only ones you have to work out this long way are the ones that say do the definition of derivative. I think the only ones are the ones I'm going to give you right now. So I'm going to tell you that I want you to do 1 over x, and it says this on your assignment sheet, 1 over x, and do square root of x by the definition, the long way. So I want you to do both of those just the way we did x squared and x cubed. So I want you to do both of those by the long way, and then I want you to do the homework that it lists there for 2.2. Okay, so it's actually I think it's written out there on your thing. So it says 2.2 gives you problems to do, and it says do the derivative of 1 over x and square root of x by the definition. So there might be some on the homework that say to do the definition, but I don't think there are. I don't think. But if there are, do it. If it says. Otherwise, if they give you, I think they give you some of these. I think they give you some of these here. I think they give you something like this, where they tell you to find, I think it says find a formula for f prime. So what they're wanting you to do is just, 5 times x minus 4 to the 4th. That's a formula for f prime. So they're saying use the shortcut there. Okay, so I think those in the book, you're doing the shortcut most of the time for those. Okay? All right.
sheet with the chapter 2.
Yeah, anybody else need the assignment sheet
Who drinks
for chapter 2?
Average. Yeah, doesn't taste good. Bad. No, it doesn't. Smells terrible. It looks bad. It looks bad. There's everything. You get stains.